Can you see my screen?
Yeah, we can see
Yes.
if you enhance your uh, for having the total screen, okay, okay. So thank you for being here. We continue with the session, the first session of this symposium, and the next talk will be presented by Valentina Sneha. The title of the paper is numerical, yeah, numerical simulation of cadmium-free strontium titanate electron transport layer in antimony sulfur selenium solar cell. This work is authored by Valentina Sneha, Aruna Devi Rasu, Claudia Elena Perez, and Lata Marazan. So please, Valentina, initiate your presentation.
Yes. Good afternoon, everyone. I'm glad to present my work entitled Numerical Simulation of Cadmium-Free Strontium Titanate Electron Transport Layer in Antimony Selenium Sulfide Solar Cells. Let's move on to the background of the study. The Sun delivers nearly 3,850 petajoules of energy to Earth each year, which is more energy in 1 hour than world consumes in a year. Converting this abundant energy into electricity efficiently and sustainably is a priority globally. While crystalline silicon dominates the PV market, it still has efficiency and flexibility limits. So further, other alternatives like um, CIGS, CDTE, um, perovskite solar cells have emerged as an alternative, but still they also possess some disadvantage like cost, stability, toxicity concerns. Hence, there is a need for a low cost, flexible, and environmentally safe solar cells possessing all these optical properties of the studied materials. Hence, we have proposed group 5,6 chalcogenate, which are recently gaining attention uh, as an alternative for the aforementioned materials. These materials are earth abundant and non-toxic. These are of generic form A2X3, where A consists of antimony, bismuth, and X consists of sulfur and selenide. These are earth abundant and non-toxic elements, and specifically, we are working on antimony selenosulfide, which features as a one-dimensional crystal structure which favors the transport along 001 orientation. And further, they have a tunable band gap and they also possess high absorption coefficients. Despite having this efficiency of 10.7, which is achieved within 7 years, the PCE still lag behind the SQ limit. So the challenges are PC being less than SQ limit. And further, another problem is the commonly used cadmium sulfate ETL, which also provides good band alignment, but it suffers from structural incompatibilities with the absorber, and it also further has a structural incompatibilities and toxicity and interdiffusion of cadmium at elevated temperature also poses further challenges in applying these. Um, Recently, other studies like including oxides like titanium oxide, tin oxide, and zinc oxide are found to be safer alternatives, but still they are chemically less compatible with the absorber, forming dangling bands and the trapped states that promotes the Shockley-Hall recombinations, which lowers the VOC. Hence, in our study, we proposed strontium titanium oxide to be an alternative which possess good properties like wide band gap, which is suitable for the electron transporting, high dielectric coefficient, and better lattice match with the absorber that reduces the interface defects and better enhancement of charge extraction. So in our study, we employed SCAPS-only simulation. SCAPS-only is a one-dimensional solar cell simulator developed by University of Gent, and it helps to carry out the detailed study of material function of entire solar cells, which is basically based on the Poisson's and carrier continuity equations. And using this, we can predict the JV characteristic, generation, recombination profiles, band alignment, etc. So initially, we have fabricated our base device structure using this configuration. The general working mechanism is the absorption of light when light passes through the electron FTO and electron transport layer, that is strontium titanate, and reaches the absorber, where the absorption of light takes place, and charge carriers are generated, where the respective charge carriers are separated and transported through the HTL and ETL and collected at the respective contacts. And this is the working principle of the structure proposed. And then we have the parameters that have been used in simulating the baseline device. These parameters were taken from the experimentally reported values for each layers. And these are the different defect states, that is bulk and interface defect that we have introduced in the layer in order to reproduce the real time and realistic results in order to be consistent with the literature. Once the baseline device has been replicated, we have extracted the JV characteristics and QE to study the PV parameters and variations in the structure after introducing the strontium titanate. From the JV characteristics, we can see that the efficiency has increased to 14%, which supposes the experimentally reported benchmark of 10.7, owing to the improved quantum efficiency. And on analyzing the quantum efficiency plot, there is a reduced response in the UV region due to the front recombinations and near unity quantum efficiency in 400 to 600 nanometers, indicating a minimal surface recombination and gradual decline at the longer wavelength, reflecting bulk recombination within the absorber. And the sharp drop near 850 to 900 correspond to band edge of the absorber. So these results indicate that strontium titanate provides excellent optical transparency and reduces both surface and bulk recombination compared with series-based devices. Then further, we have attempted to optimize the layer parameters of strontium titanate, that is thickness has been varied from 0.01 to 0.1 micrometers, and the donor density has been varied from 10 power 12 to 10 power 20 centimeter per cube. So these are the results that has obtained for varying the ETL thickness, that is on varying from 0.01 micrometer to 0.1 micrometer. There is an increase in the VOC fill factor, a decrease in the VOC fill factor and the PCE, whereas JSC increases slightly on increasing the thickness. This occurs because as ETL thickness is increased, it raises the series resistance and recombination losses even though the coverage improves. And the increase in the JSC may be attributed to the better charge collection efficiency due to the improved physical coverage. However, thicker ETL increase recombination and resistance as seen in the recombination plots. We can see at thicker ETL, the recombination is higher, where it has drastically reduced at 0.03 micrometer. Further, we have extracted the JV plot for the lower and higher thicknesses, where the JV curve shows superior performance at 0.03 micrometers. And from the design perspective, experimentally, a thinner ETL than HTL is preferred, and also since electrons have a high mobility than holes, a thicker HTL ensures balanced charge extraction while suppressing interfacial recombination. Hence, an optimal thickness should be greater than 0.02 micrometers, since lesser than this thickness might induce a pinhole effect. Hence, 0.03 micrometer was shown to be consistent, suitable thickness, which is consistent with the literature. Then we have varied our ETL donor density, which is varied from 10 power 12 to 10 power 20. And on analyzing the result, as donor density increased, the PV parameters remained constant up to 10 power 17, whereas after this, there is a drop in the VOC, there's a drop in the JSE, where there is an increase in VOC fill factor and PCE. So the drop in the JSE is due to the wide band gap of the strontium titanate, ensuring minimal light absorption, and a slight decrease likely arises from the electric field redistribution at high doping, which affects the charge collection. And then, in order to observe these changes, we have extracted the generation rate plot and the electric field. From the generation rate, we can see that there is a drastic increase in the generation rate at the higher donor density compared to the lower donor density. Similarly, the electric field distribution has drastically increased in the absorber region at the higher donor densities of PTL, whereas it has been reduced to the lowest at the lower carrier density. Hence, we have chosen 10 power 20 to be the optimal range. Moving on to the comparison of final device. So after optimization, we can see that there is a drastic increase in the JV characteristics, whereas PC has risen to 21 percentage, whereas initially it was 14 percentage. And also all the PV parameters has been increased on analyzing the JV characteristics. Further, in order to confirm this, we have extracted the generation rate of the initial and optimized device, where we can see there is an increase in the generation rate after optimization, which is about 10 power 22 magnitude increase has been observed after optimization. And further, we have extracted the energy band diagram before and after optimization. From the optimization, we can see uh, that there is a small cliff type barrier observed in the conduction band offset, which enhances smooth electron extraction. Also, from the valence band, we can see that a large spike that blocks the whole diffusion into the ETL. Hence, also from the Fermi levels, we can see that the quasi-Fermi level separation which collectively enhance the charge collection. Then we have varied the temperature and light intensity. The device stability was analyzed under different temperature like 300 to 450 Kelvin and illumination intensity of 100 to 1000 watts per meter square. On analyzing the temperature variation, the VOC and fill factor declined due to enhanced SRH recombination, whereas JSC rise marginally uh, due to the band gap narrowing effect at the higher temperature. And further, on analyzing the variations with respect to the illumination intensity, the VOC and JSC increases. JSC increases linearly and VOC increases logarithmically, which is an expected performance as reported in the literature, which is due to the photocarrier generation changes and Fermi level splitting. And the fill factor and PCE consistently increased at the increasing intensities. So these behaviors confirm that optimized devices maintain good operational stability, and it also maintains predictable photo response consistent with the literature. Conclusion. In this study, we have proposed strontium titanium as an alternative to cadmium sulfide as an ETL, which demonstrates efficient performance using cap-only simulation. And after optimization of ETL thickness and donor density of the strontium titanate, the efficiency increased from 14 to 21 percentage, mainly due to the better enhancement in the VOC and fill factor. And further, the enhancement in the JSC confirms that the material has good optical transparency. Further, from the energy band alignment and electric field distributions, we have the, there is a better alignment and strong electric field observed due to the reduced VOC loss around 0.39 volt and the device being stable under varying operating conditions. Hence, we believe that this work will serve potential alternative to the cadmium sulfide as an ECL. These are the references that we have followed. Thank you for your attention.
Okay. Thank you, Valentina, for your presentation.
Thank you.
We have some time for questions. Please, one question. No questions? Okay, then I will make one question. When you do simulation with the SCAPs, usually you will get unrealistic results unless you provide realistic values for the parameters that you are using in your simulation. And so, since for these materials, new materials, you don't have measurements in order to have realistic values for the parameters, you will get, as a consequence, non-realistic results. Okay? And for example, if we go to your slide where you show your recombination parameters, the volumetric and the interface.
This one?
Yeah. You can see that, for example, for the absorber effect parameters, you assume values of 10 to the 12 or 10 to the 13 for the defect density. This is a very low value. This is not realistic.
No, actually, these defect levels are directly taken from the experimental report for this material, absorber material. So, as I mentioned, for this 10.75% maximum efficiency, so based on that particular report, we have selected the defect densities. From the photoluminescence value, they have reported the defect densities for this particular material.
So somebody measured this defect density in your material?
Yes, all these values are based on the experimental results.
So these are measured values?
Yes.
Okay. And similarly for the interface defect densities, okay, 10 to the 14, is not so low, but it is small, as can be expected for the interface with some ETLs, electron transport layers. Okay, so unless you have realistic values, you will not get realistic results. Okay, so try to or either measure your parameters,
okay,
and then simulate with realistic values, or try to find those values in the letter, as you say that you did for this case.
Okay, sure.
Okay, thank you.
Thank you.
Okay, then since is there any other question? If not, let's thank the speaker. Thank you.
Thank you.
So we have still two papers to be presented. The next one will be presented by Ashok. And the authors are Ashok, Jorge Baristo Conde, Francisco Javier Cano, Mauricio Ortega, Odín Reyes, Miguel Ángel Luna, María de la Luz Olvera, y Arturo Maldonado. And Arturo Maldonado. Okay. And the title of this talk is Explore the Impact of Copper Gallium Selenide Black Surface Layer on the performance of the copper indium selenide PV devices through the theoretical model. Okay, please, Ashok.
Thank you very much, Doctor. Thank you very much, all of you here for my presentation. So this work is like the same similar means the similar the Valentina who spoke about the scabs. This is the scab simulations about the copper indium selenide solar cells. Here I have like introduced a new concept where the impact of the copper gallium selenide back surface in there, on which I will discuss later. But this one is the main idea of this work. But these are the contents which I'm going to present like step by step. So before starting the design, so I would like to start about the little bit about the copper indium gallium diselenide solar cells, which is the second generation solar cells. And normally we are having this kind of solar cells is the stack of the different layers. So normally they use glass substrate, molybdenum is a back contact, and copper indium gallium selenide is p-type semiconductor alveolar layer, and Sirius and zinc oxide is the window layer, copper layer, you can say. And zinc oxide, almond of zinc oxide is the transparent conducting oxide, and finally front contacts. This is the like basic concept to basic structure of the solar cells. The basic concept is like what we have is in this section, not like p-n junction. So here we are having the incident light junction here. So p-n junction we have generated like electric field, or we can say space charge region. And here, like it separate the generated charge carriers. Like once it's absorbed, it can generate electron hole pairs. These can separated by the electric field generated by p-n junctions. And then after it is separated and finally collected. This is the idea. For the copper indium gallium selenide, so it has some characteristics such as direct and tunable band gap. So direct band gap helps to get the absorb the incident photons, even like a 2 or 3 micrometer of this thickness of the absorber layer, and also high absorption coefficient. It also has the like a very low thickness can absorb almost all kind means almost all incident photons, and also have the advantage of long-term stability. I think the degradation rate is 0.02% like every year. And this for the solar kind of solar cells, flexible and lightweight. So for now, we are having the record efficiency 23.6%, and all of those applications. You can also use like terrestrial as well as space applications. Okay, so before starting scabs, like why simulation study? What you can help. So simulation, like numerical simulation, you can say like it can integrate real life problems into virtual machines to provide like to efficiently analyze the complex problems, which I will simulation for this case solar cells, but other kind of the complex problems also can do. So these like here I have highlighted some advantage of simulation. It is like it's easy to optimize any real-time design problem without physically building it real test environment. So it is not needed any laboratory to do experiments. So it prevent it prevent to high cost as well as time. Also, it can interpret the semiconductor devices, physical problem, complex problems also, and also design the semiconductor basic equations. Like normally, it can have the Poisson's equations continuity equations for charge carriers, and it can produce non-linear equations for modeling solar cells for this, and predict the outcome of a matter property. And the most important is explore the new devices. It can explore new devices and cheaper and quicker. No, these are the advantages. So there exists for the solar cells, there are different kinds of simulators. PC1, the SPSA. Here we have like the availability dimensions and system requirements and capability. And which kind of simulators can have which can simulate which type of solar cells. So, I'll focus on these caps. So here we normally focus on normally it is developed for the copper indium gallium selenide. So later it is developed is strengths to different kinds of other types of solar cells, even like tandem solar cells can do. And here also more, we have having 1, 2D, 3D. These are all examples of the simulators. Okay, so these caps normally it is solar cell capacitance simulator. So once you open these caps, like we are having this display. So I think it is not very high quality, but it's kind of see. But what is the thing is that you can have like options to get like different kinds of illuminations. Here is I think resistance you can include, and you can set the problem here. So once you click here, you will get this display. So in this display, so here we are having the like facility of the you can include 7 layers, and even like you can include here after clicking here, you're having facility to introduce their battery parameters, like the properties and everything. So I think this way I input, but you can see this is the this you can see in this caption that it's easy, like you can see it's freely available in online and compatible with Windows and Linux, versatile in modeling solar cells, as I mentioned earlier, that you can have and explore new designs of solar cells. Okay, so these are I have previously worked with based on these caps with using like CIGS and I think different buffer layer, different observer layer, CIGS. Even though like CIS, I have here in this case only optimizations. So in our case, having this exploration of the back surface field layer. Okay. So the main idea of this work is like why we use the back surface field layer, no? So the idea is using is once we use it can create that electric field which can impair the magnetic charge carriers, for example, electrons, no, like in this case. So it can so that the magnetic charges goes toward the space charge regions, it can have a chance to separate and get the more collections. So this is the idea. So you can that's why like it can increase the solar cell parameters. So here are some promising BSM methods for copper indium gallium based solar cells. So here we'll normally discuss about copper gallium selenide. Okay, in simulations, like structure what we use the back contact, CGS was CGS like copper gallium selenide, and CIESC copper indium selenide as earlier, CDS zinc oxide earlier, and the zinc oxide and the transparent carbon dioxide. And these are the parameters what we use. These parameters we have taken like previously published study and or like our work, no, like. So here we have varied the thickness. We have primarily focused on thickness and carrier concentrations. So later I will discuss about the effect of these parameters on the solar cell parameters. Okay. So here we have initially vary the thickness of the copper indium selenide thickness. All other parameters like kept constant based on the optimized results. So in what we have done previous work, what we have done, we have varied the one micrometer to 10 micrometers. So in that case, we wanted to focus on more details. So what we change is the range 500 nanometer, 1000 and 1500, like similarly to 6000. So analyzing the results, what we have is like all the parameters increasing with increasing thickness. What happened? So once the thickness is increases, the incident photons have a longer time to interact with the materials, and it's essentially helps to generate the more electron pairs and increases the source current circuit, GSC, circuit current density. Sorry. So then after once it is increases, we know that the open circuit voltage is directly related to the circuit current density, which is natural logarithmic to circuit current. So once it is increases, so its value VOC also increases. So it is all related, and finally efficiency is increases. So after the, I think five micrometer, so there is variation, but very little margin variation increasing. So we have to get it the optimum conditions. So next we checked on the copper concentrations. Similarly, what we have is initially in this case also we have varied 15 to 16, but the vary is 2.5 to the power 15. So what happens? So lower concentrations can so with increasing, it can increase the properties and the properties. So it is increasing the VOC value. But after at high values, what happened? Semiconducting property like it can have more defects. So it started to decrease the factor, and then consequently efficiency impacted. So maximum efficiency what we have is I think 10 to the power 70 or 75 to the power 16. These two conditions have the best results. Next, we check the CDS thickness. We know that like buffer material or window metals should have low thickness as possible, so that the incident photons can pass through absorber layer and have to participate in the generation of the charge carriers. So here, so that's why we have focused on the very low thickness of the CDS thickness. So initially, very low thickness you can have very low efficiency. These two parameters, what happened? A very low thickness might have the like very sorry decreasing the sun resistance. So you might have this alternate path for the general charge carriers. So it can decrease. So after that, so we are having the increasing the efficiency. So best one we have found 70 nanometer for the CDS thickness, and for the concentration, as for the publications, like normally Windows material or buffer materials should have high carrier concentrations compared to absorber layer. So in this case, similarly, after the higher value of this, we're having the high efficiency increasing. What happens with higher concentration? It can help to increase the space charge region in the towards the absorber layer. So it can have increase the absorption of the incident photons, generation of charge carriers increases the current density. This is the result. After that, after these high values, the efficiency is constant. Okay, so in this case, BSF, so copper gallium selenium BSF materials, so thickness we wanted to check. We didn't want to put more like a lot of thickness because with increasing thickness, cell resistance will increase. So similarly, we have checked 120 to 100 nanometer, and here we are having the efficiency of like the parameters. Normally open circuit voltage, short current is almost constant. Open circuit voltage is increasing after 150 nanometer, and after 500 nanometer, I think the changes is very small. So we have kept the 500 nanometer as the optimized conditions. So in this case, similarly, for the BSF concentration, we have increased we can see the increasing concentration. For this case, for BSF material should have high concentration. Why? Because with higher concentrations can have, like, for example, whole concentration can be help to formation of ohmic contact. So that's why, like, with increasing carrier concentration, so it is increased high value, I think up to 32%. Okay, so here using and not using BSF layer. So what it is these two, it shows like the efficiency. It shows like you up to 32%, almost near to like soft leakage limit, like for single junction solar cells, it reaches to 33%, around 33%. So it using BSF materials, it can have, although it is ideal conditions, means like we can say like this can happen. No, these are the ideal conditions, but using BSF material can have potential to increase the efficiency. So here we can say without BSF material, we have checked the IV curve, and we have without BSF materials, so the efficiency was 22.46, and after using it is to 32.60%. So the increment will be 10%. You can so almost more than 10%. So what happens? So after optimizing this, these are the, like I said, ideal conditions, like theoretical parameters. So what I wanted to, I have some parameters, like I have experimental parameters which we have done in our lab. So we wanted to use this parameter. What happens? What happens? It will, how it shows. So for example, CISC, which we have deposited the hybrid method, like escape parameters and co-evaporation method, and CDS is, as we have in CDS 5 conditions, which we have worked at different time using chemical biodiversity. And these are the parameters, experimental parameters we use on the ideal case. So for this case, initially we check for the solar cell conditions, like healthy condition, we check without BSF method. What happens? So in the series, we can have the thickness, like for example, for 20 minutes, 40 nanometer, 80 nanometer, and then so on. So we can see the results, like using these parameters. Series thickness has a greater impact on the solar cells, because with increasing thickness, we are having low efficiency. I think less than 2% with increasing thickness. So what we have, we can see that without BSF, using BSF layers, series thickness has greatly impact with the performance. But what happened if we use using with BSF? So with BSF, although like it is decreased with the effect of series thickness, but not much, like not to 20 to 1%. Like here we are 30 to 37%. So
One minute, because we need time for
Okay.
questions.
I almost finished that. So this one, what I wanted to using BSF has the chances to improve their efficiency, and these are the conclusions. But these are based on my results. I would like to thank to all these who helped me in my investigations. Thank you very much.
It's okay. Thank you. Please, do you have any question? No questions? Okay.
No, indeed.
Okay. Okay. Fine. Okay. Then if there is no questions, I have this. As I mentioned in the preceding presentation, different from that presentation, you then show the recombination parameters. And that's why you get as a maximum efficiency about 32% efficiency, because you are taking almost ideal values for 32.6 is about the Shockley-Queisser limit for these materials. And so you are taking unrealistic things in order to do your simulations. And I suggest you to look for realistic values in order to put in this kind of programs. Okay?
Okay.
But you associated the thickness of the cadmium sulfide, and you show if we can see
Yes.
the results.
This one? Or you can say-
No, when you show the efficiency results as a function of the cadmium sulfide thickness.
So initiate, I guess.
Yes, and you said that the low values for the small thickness is associated to the
To the sun resistance, like low value is it decreases sun resistance. So it can have alternative path to
how PC1 SCAPS one determine the shunt
no,
resistance.
this one I just like I analyzed, like I have checked on these other place, other papers. I just like I wanted to tell like this lower thickness might have this kind of like can have a alternative path because low thickness 20 nanometer, 30 nanometer like is almost impossible to in experimentally to get, you know.
Yeah.
And even if you get, so it might have some defects on the continuity, or you can say have some alternative path for regenerative susceptibility. That was like that one because because in this case is very low, so that might be reason like that was the reason because I have like checked
The shunt resistance is an external parameter for the simulation. It's not a consequence of the
no,
the
no. For the simulation, like yes, no. But like for the explanation, like to have this, it might be like to in low thickness, so might have these defects. I wanted to.
Yeah, but you are only varying the thickness.
Yes, maybe next time I will check on the simulations about because there is option also to get some resistance and resistance so that I can have more ideas about this bit of this thickness.
Yes, you have to analyze why you got this result, but it is not related to the shunt resistance. Okay.
Practically, yes.
Not because you are only varying the thickness. Yes, the cadmium sulfide. You are not having any relation with the shunt resistance unless you put the values
Yes.
of the shunt resistance.
Yes.
Okay.
Thank you.
And then you do any calculations as a function of the doping of the donor acceptor concentrations. Yes. Can you tell me how you would vary those things in this kind of materials?
For example, serious, no? Serious.
Even CDS.
Yes.
But usually it is not so easy to
To
vary the current concentration in cadmium sulfide.
for example, yes, but means I have some here.
Because in a simulator, it is very easy to change things.
Yes, exactly,
Okay.
exactly. So in this case means shear, like we can change means different deposition times.
Yeah.
Temperature.
Okay, those are your experimental.
Yes, these are the
results. But you made your simulations varying these
one.
values. And please explain to me how you do this. Show me one of your graphs.
Yes.
Where you say concentration.
Here, no?
Yeah. How would you vary the concentration from 10 to the 16 to 10 to the 18?
In simulation.
No, in the simulation you can do it,
Yes.
but in the practice,
It's practice.
Yeah.
Yeah, this one like, for example, for serious material, but I use the chemical deposition method.
Yeah.
So there I have used area and the cadmium acetate, aluminum acetate also. So it's like a reagent. So in this case, like what I have initially done, like in my practical experience, what I have initially done, like varying the cadmium acetate using the same concentration of the area. So using the cadmium, like increasing the serious acetate, this cadmium acetate precursor materials for this case can increase, like from my experience, like what I have found, it can increase the cadmium concentration.
hey, I have done many experiments with cadmium sulfide. And if you
What
can
you have
change
done, like
the
did you
cadmium
use
concentration.
aluminum acetate of them? Did you use consider as like a reason? Because I use only messages. Yeah, that's why like it can have.
Okay, if you can show that you can vary experimental in this range, I will agree with you. Okay, but I don't think so. And this is only one example. It's the absorber, the copper indium gallium selenide or copper indium selenide. It is also very difficult.
Yes,
And
because
so in a simulator you can do whatever you want.
yes,
Okay, but in the real thing, this is not.
look, yes, yes, you are right. What I wanted to do is like for doing simulations. What I wanted to find the optimum what will get optimum value so that I can start practical work in that place. I can try to get that one. That was my idea.
Okay, okay, thank you.
Thank you.
One of the girls has a question. So we,
There is one question.
Yes.
Online.
You can read.
just,
Why did you?
Please read it.
why did you use SCAP software for simulations of solar cells? Why other software is possible to get similar results? What makes SCAPs better or different compared to other? And about the BSF layer, does copper gallium selenide bring any specific benefit?
Okay, thank you. Yeah, I will do it very fast. For example, for these caps, like it is free, no, it is freely available. Another thing is it is initially developed initially for the copper indium gallium selenide. So it is primarily it is for the copper indium gallium selenide, and also it has benefits of the you can use in Windows or Linux or are simple to use. These are the benefits. For the VSF, why I chose this metal copper gallium selenide because normally in our lab, like we use the coaxial metal copper indium gallium, and we have the precursors. So if we can deposit copper indium selenide, we can also deposit copper gallium selenide. So we don't need any extra material or extra means other equipments or thing, so that we can have better to use or handle. That's the secret. Okay.
Okay. So thank you, Ashok, and let's thank. So we have the last one.
Uh, uh, I had a technical problem. Present now.
I think it's another.
Can you hear me, sir?
Who are you?
I'm Maush Abd Haq, the second presenter in this room.
I am sorry, but we were waiting for your connection.
I had a technical problem.
A different
My
program?
connection is very. I'm in the second position
Yeah,
in
but
this room.
we cannot. We have to continue with the presentation that is going to be presented, and
Yes.
and then the audience have to say if they want to hear your presentation. Because
Okay.
we are not. We understand your situation, but also people here have to agree because we were waiting for your presentation.
So if you cannot,
Okay.
What can I do?
Okay.
What can I do?
Wait
So,
for the next.
Wait.
Wait for the next presentation, and then
Okay.
will be the last one of the program, and then
Okay.
we will ask.
Wait. Yes, I'm waiting. So.
No. Okay, the topics of this presentation are why perovskite solar cells research is important today. I talk about the fabrication of solar cells by spin coating method with two different hole transport layers, the common and reference spirometer and a copper fission atom. And I show the JP cell characterization and methodology for the electrical parameters determination, the discussion of the performance limiting effects for whole transport layers, and the future work and conclusions. We talk about the hybrid perovskites. Perovskites in general is a family of different materials with different properties. In particular, for solar cell applications, we focus on a particular elements composed to the perovskite materials with the structure A, B, X string. In particular, as a site, we have an organic or inorganic cation, can be methylammonium and formamidinium as organic cation, and inorganic cation, we can use cesium and rubidium. In the B side, we find a big organic cation like lead and tin. And finally, in the X positions, we can use different halogenanions like bromide, chloride, and jodide. And why perovskite is so interesting to use in solar cell is because of perovskite materials possess a high absorption coefficients, similar to technologies like gallium arsenide, gallium telluride, and another important technologies. In particular, present a low value of Urbach energy, and this represents a material with low energetic disorder. And another important property of perovskite materials is related to the enable band gap, cationic or anionic substitutions. This is, with this property is possible to enable applications in tandem solar cells. And this material presents a small excitonic built-in energy, and it's relatively easy to separate the photoxide carriers at room temperature. And in particular, one important properties of this material that is possible to fabricate with low cost process. In particular, some process to fabricate perovskite thin films is one step precursor deposition, two-step sequential deposition, dual source vapor deposition, and vapor assist solution deposition is a material with many possibilities. In particular, the device that in literature is possible to find device fabricated with this material, and in a focus of these charts about the last years, it's possible to find interesting results with perovskite with maximum power conversion efficiency similar to silicon technology in a single union, and with related to the tandem solar cells, it's possible to find very interesting results in comparative with 3,5 elements with silicon. And of course, the perovskite technology have different challenges to find solutions. In particular, we find insufficient stability under real operating conditions, difficult scalability for large-scale industrial production. Of course, the use of leads, the toxicity limits commercial acceptance, and it's possible to find interface-related losses, which reduce both efficiency and long-term durability. In particular, in our laboratory, we work with a particular hybrid perovskites, and we make the NIP solar cell structure using a a transparent oxide conductor, an electron transport layer, the hybrid perovskite, the whole transport layer, and the metallic contact. In particular, the whole transport layer is an important layer because help to the transport of the holes through the device. Some properties important for the whole transport layer are the valence band energy level must be properly aligned with the perovskite, and we need a big difference on conduction band in order to block electrons. And this material need a high hole mobility and a low resistivity. And finally, we need a material with a photochemical and thermal stability. In particular, in our work, we're working with a perovskite little different from the standard methylammonium lithiodide. This is the compound. And in particular, we use the formamidinium organic because give a more stable perovskite than methylammonium. And when we use a small amount of cesium, improve the stability of the materials. In the case of the whole transport layer, spirometers is the reference on the solar cells, but spirometers is very expensive and require complex processing, while copper titanium atom is an inexpensive and simple to process. In particular, in our laboratory, we're working with the two-step deposition methods. In the first step, we deposit by spin coating in a homemade glow box a solution with lithiodide and cesium iodide. We perform a rapid annealing, and as a second step, we deposit by spin coating formamidinium iodide solutions. And with a process of annealing, we obtain the perovskite complete. Some properties of the perovskite that we make in our laboratory are the present and direct path gap from tau colloids with a value of 1.54 electron volts, and this is a suitable value for a solar spectrum. In the case of the crystallinity structure, we present an alpha cubic phase of the perovskite thin film. In particular, we have a leadership of the lattice parameter in comparison with a pure formamidinium perovskite, and it's possible to estimate a proportion of cesium on the molecule around 5%. And the morphology properties by scanning electron microscopy, we obtain a uniform morphology of the material with a grain size about 500 nanometers. Finally, by energy dispersive spectroscopy, it's possible to estimate an atomic proportion of the cesium around 6%, and is a value with similar to obtain by X-ray diffraction. For the fabrication of the whole transport layer, spirometer is a very complex material to fabricate. Why? Because of the spirometer solutions needs two dopants to increase its electrical conductivity. We need a lithium salt and need a thermethylpyridine to stabilize the lithium salt. And a second step, we have the spin coating deposition of the spirometer thin film. And final, we need a process of oxidation in order to spirometer reach adequate conductivity values to work as a whole transport layer. In particular, needs a chamber free of solvents, far from UV light, need a dry ambient, and a process around 12 hours. It's many times. In comparison, the copper titanium atom deposition is a simple, a quickly process with the precursor solutions, the deposition, and a quickly annealing about 10 minutes. And it's a simple process without the use of dopants or additional oxidation process. Finally, in our device, we need a metal contact. We use gold evaporation with a thickness about 80 nanometers. And we, in a substrate, we fabricate, or we have 16 solar cells. Each point represents a device in our substrate. And these devices are defined in each substrate by means of a metal mask during the evaporation, and the device are separated by mechanical screening. And we can see on these lines this separation. And finally, when we make these devices, we compare the performance of the devices with spirometer and with copper fusion atom. And we can see in these charts the parameters. We compare the open circuit voltage and the short circuit current density. And we can see that spirometers with the blue chart represent a better value of open circuit voltage. The same situation occurs with the short current density. A similar behavior we can see on the field factor. And finally, we can see a much better power conversion efficiency of the spirometer devices in comparison with copper fusion atom. And it's clear that the spirometer layers exhibit a better photovoltaic performance compared with the fusion atom layer, with a average power conversion efficiency of 10% for spirometer in comparison with 4.5 power conversion efficiency of the copper fusion atom. However, it's clear that the spirometer is better, but it's important to understand why is the reason to this to this to these results. In particular, there are the JP curves for each fault transport layer. Clearly, a maximum power conversion efficiency with spirometer around 12% and a maximum power conversion efficiency with copper fusion atom about 5%. In particular, in order to understand what's the reason to the difference in the performance, we working with a model based on the electrical model of the solar cells on the illumination. The equation represents this electrical model, and this is the equivalent circuit of the electrical model. The parameters important to know, additional to the classical parameters, the photovoltaic parameters, are the JL, illumination current density, J0, saturation current density. We need to know the serial resistance, and we know the shunt resistance. In particular, we're working with the next analysis method to obtain these parameters. And we assuming a single exponential that current component for a solar cell on the illumination. In particular, we use ideality factor equal to 2 for perovskite solar cells. With this equation, it's difficult to indicate. We obtain two other equations in order to know the J0 and the JL parameter. And with different conditions, it's possible to establish two equations. And we use an iterative method in order to obtain a value of J0 using the value of J0 into the equation of the JL. And a similar process with a new UL value, we return to the first equation, and it's possible with 2 or 3 iterations obtain appropriate values for J0 and JL. And finally, in order to obtain the shunt resistance and the series resistance, we use the inverse of the slope in the JP curve in different points. For shunt resistance, we use the point of voltage equal to 0, and for series resistance, we use the point of voltage is equal to open circuit voltage. Well, with this method, we obtain another important parameters to study the JV curves of each Hall transport layer. We can see for copper fusion atom a bigger value of series resistance 23 in comparison with a value of 10 of 10. And we can see different shunt resistance, a bigger value of the saturation density current for copper fusion atom in comparison with spirometer, and a low similar value of the illumination current. But it's important to understand what represents each parameter. In particular, if the comparison of the saturation current density, we can say that the direct combinations current for spiro cells is almost two orders of magnitude smaller than the copper fusion atom cells. This means that the spiro generates much less
interface density of the states than copper-tungsten atom in contact with the perovskite. It's important the interface between the perovskite and the hot transport layer. For the same reason, the illumination current density, JL, is less for copper-tungsten atom cells in comparison with spirometad cells. And the point number 3, we can see a bigger factor of the series resistance, and the whole transport layer thickness for copper-tungsten atom must be optimized or reduced. And the resistivity of the copper-tungsten atom must be reduced in order to obtain a better value of the series resistance. And finally, we can see in the point number 4 and point number 5, the copper-tungsten atom deposition affect the perovskite characteristic, causing an increased current leakage, smaller shunt resistance as compared with the spiral deposition. And in particular, in general, the whole transport layer deposition must be improved to avoid this. In particular, we obtain a power conversion efficiency with the spirometal layer around 12%, but this value is possible to improve with a better deposit of the layer. It's important to have the better values of series resistance and shunt resistance in order to obtain a better efficiency. According to our analysis, with better resistance values, it's possible to obtain a power conversion efficiency about 18%. And with this kind of facts, we working to improve the copper-tungsten atom deposition in our laboratory, and in recent results, we obtain an improved power conversion efficiency. We talk about the initial values about 5%, and we reach currently we reach values around 10% with the improves of the copper-tungsten atom deposition and the better properties in the layer. As a conclusion, the perovskite solar cells with copper-tungsten atom and spirometad were made by spin coating deposition. The perovskite was deposited in 2 steps. In particular, solar cells with the spiro obtain better efficiency in comparison with copper-tungsten atom. A quick analysis method is useful to develop and understand better the results and the main electrical characteristics difference for whole transport layer are now understood. And it's possible to improve the solar cells with both whole transport layers. And it was shown that once the low field factor is improved, efficiency around 18% will be achieved. And a knowledge of the perovskite solar cell team and the 2 other institutions. This is the team working in our laboratory. And that's all. Thank you very much.
Thank you. Oh, we have time for 1 or 2 questions.
Thank you for the talk. I have wondered about the thickness of your perovskite on the whole transport layer.
Okay, perovskite have a thickness about 500 nanometers, and the spirometad transport layer is about 200 nanometers, and the copper-tungsten atom initial are around 100 nanometers. This copper-tungsten atom is important to reduce about according to our analysis.
Thanks.
Okay, another question? No, I will not make any question. Thank you. Also, let's thank David for his presentation. Okay, I don't know if you want to hear at least 1 or 2 talks that were suspended by a failure in the connection. The authors of these 2 talks are now ready, it seems.
Yes.
Yeah?
Yeah.
Okay, then let's see, Mr. Tarek. Are you there?
Yes, I'm Mausha عبد الحق.
Oh, okay. Maucha.
Okay. Yes.
So you will present the 2 papers?
The 2 papers, yes, instead of my colleague Tarek Barghouth.
Okay. So please try to adjust your time. Okay. So please, we are going to start with the first one. It was already presented at the beginning, but
Yeah. Yes.
you will have to repeat the boosting
I-
short circuit current in
Yes.
perovskite solar cells through gold nanoparticle incorporation.
Okay. Okay. Is my screen shared in your desktop? Are you
Yes, we
hearing
can
me,
see.
sir?
Yes.
So I will present from the beginning.
Okay, listen, Hans. Okay. Okay, now we are ready.
So the structure of the presentation is outlined as follows. We will commence by an introduction. Following that, we will present the device and modeling methodology. Now, dataset description and deep learning analysis. To conclude, we will summarize this presentation by offering some insights and discussing potential avenues for future presentation. Perovskite solar cells have attracted huge interest because of their high efficiency and low fabrication cost. However, lead-based devices raise environmental and stability concerns. Tin-based perovskites, such as formaldinium tin triodide, are promising lead-free alternatives. The challenge, however, is the oxidation of the tin, which create defect and reduce efficiency. To address this, we propose incorporating gold nanoparticles, which can enhance light absorption through plasmonic resonance, leading to improved current generation. Here you can see the structure of the simulated device. It consists of a glass substrate, transparent conductive oxide, electron transport layer, a formaldinium tin triodide absorber, a Hall transport layer, and a back electrode. We embedded gold nanoparticle into the absorber to study their plasmonic effect. For electron simulations, we used SCAPS1D. For optimal analysis, we used FDTD simulations. Together, these tools allowed us to study both charge transport and light absorption. Employing SCAPS1D software for simulating semiconductor property, in our simulation, we varied several parameters to understand their impact. These include absorber thickness, ETL and HTL materials, doping concentration, and the radius of the gold nanoparticles. The main output metrics we analyzed were open circuit voltage, short circuit current, fill factor, and overall power conversion efficiency. To validate the simulation accuracy, the current voltage characteristic produced by SCAPS were compared with the experimental measurement. As illustrated in this figure, the strong correlation between simulated and measured results confirms the reliability of the modeling approach in physical behavior of the solar cell. The results show a clear improvement in short circuit current without nanoparticles. GSC was as low as 5.41 milliampere per centimeter square. With optimization, especially with the titanium dioxide as ETL, and properly sized nanoparticles, GSC increased to 30.91 milliampere per centimeter square. Interestingly, the choice of HTL had less effect on performance. We found that the optimal nanoparticle radius is in the range of 10 to 20 nanometers, which maximize plasmonic scattering and absorption. To perform the deeper analysis, we built a dataset from 1,638 simulation runs. Sorry. The dataset include both categorical and numerical features such as ETL, HTL, nanoparticles reduce, doping concentration, and thicknesses. The target value was the short circuit current, which an average of 23.94 milliampere per centimeter square and the maximum of 13.91 milliampere per centimeter square. This dataset allowed us to train a machine learning model for predicting and interpretation. We use a deep neural network regression model to predict short circuit current improvement from the variation. The network had multiple layered ELU activations and was trained with Adam Optimizer. To interpret the result, we applied shape analysis and ablation studies. Both methods identified nanoparticle radius as the most dominant feature, which confirms the strong role of plasmonic enhancement. The shape and ablation importance score are plotted side by side for comparison. Nanoparticles radius had the strongest influence on GSC, the short circuit current predictions, followed by the type of HTL and ETL materials. Figure 4 demonstrates that the proposed deep learning approach not only provides accurate predictions, but also yields interpretable insights that can inform material selection and device design in perovskite photovoltaic. The main insights are as follows. First, gold nanoparticle in the 10 to 20 nanometer range significantly boost the short circuit current. Second, the titanium dioxide is the most suitable ETL due to its energy level alignment with the formaldinium triodide. Third, the choice of HTL is less critical. And finally, deep learning analysis validates the physical understanding by ranking nanoparticle radius as the most important parameters. To conclude, we demonstrated that gold nanoparticle can enhance short circuit current in lead-free perovskite solar cell reaching values above 30 milliampere per centimeter square. This combination of optical modeling, electrical simulation, and AI analysis provide a powerful framework for device optimization. Thank you for your attention.
We have time for questions.
Yes. I'm waiting, sir. Do you hear me?
Yeah, I can hear you.
One question.
Yeah.
What is the method to introduce nanoparticles inside of the perovskite?
The question is, how you introduce the nanoparticles into the perovskite?
How?
Yes.
We use the FTDD. Wait for me, please. Repeat the question, please, sir.
Okay. The question was,
What is your method to introduce gold nanoparticles inside the perovskite?
The method we have you did in the FDTD simulations. And we have used the parameters, optical and the electrical parameters. We introduced it in the SCAPS 1D.
Okay. Thanks.
Mm-hmm. With pleasure.
Okay. Another question? If not, then let's thank the speaker. And then we have the another presentation.
Yes, I have
Yes.
another presentation.
Yeah, by the same authors, and
same
this is
authors, yes.
performance assessment of for my medium cesium tin 3-iodide perovskite solar cells via deep learning.
Yes,
Okay.
yes, sir.
Initiate.
Okay, I will present the part. Wait for me. Is my screen shared on your desktop, sir?
Yes.
Okay. I will full screen the. So the second presentation is performance assessment of the formadium cesium tin triodide perovskite solar cells via deep learning. The structure of this presentation outlined as follows. We will commence by an introduction. Following that, we will present the device and modeling methodology. Next, we will discuss the results, dataset description, and training analysis. To conclude, we will summarize this presentation by offering some insights and discussing potential avenue for future researches. Perovskite solar cells are one of the most promising next-generation photovoltaic technologies. However, most high-efficiency devices today are lead-based, which raise toxicity and stability concerns. That's why we focus on formadium cesium tin triodide, lead-free perovskite. It offers a good optical and electrical properties, but suffer from degradation and instability. To address these challenges, we use a combination of physics-based simulation and the deep learning analysis to optimize the device. Here we see the structure of the solar cell, starting from the sport conductive oxide, the ETL, the formadium cesium tin triodide absorber, the HTL, and finally the back metal contact. We modeled this structure using SCAPS 1D, which solved the Poisson diffusion and continuity equation under standard solar conditions. The simulation was validated against experimental data, ensuring that our results are realistic. Now, looking at the current voltage characteristics, when we increase the band gap by adjusting the tin model fraction, we see an increase in open circuit voltage, but at the cost of a reduction in short circuit current. The Q factor remains fairly stable. This means that the efficiency depends on balancing these two parameters, VOC and GSC, short circuit current, rather than just maximizing one of them. From the simulation, we built a dataset with 538 entries. Each sample corresponds to a unique device configuration. The dataset includes categorical features like the choice of ETL and HTL, and numerical features such as band gap, doping levels, and layer thicknesses. The output we focus on is the power conversion efficiency, an average of the efficiency in about 13.8%, with values ranging between 7.7% and 18.8%. We then applied deep learning to analyze the dataset. After preprocessing and normalization, we trained a deep neural network with 3 hidden layers. The model accuracy with a range of 0.969. Using chip analysis, we identified which parameters are the most important, the ETL type and its done, while HTL parameters play a smaller role. Residual analysis confirmed that the model is ambiguous and robust. As shown in this figure, the most influential feature was the ETL, with a mean absolute shape value of 2.45, followed by the ETL donor density, highlighting the dominant role of the electron transport layer in determining the device efficiency. Other features with moderate to low influence include HCl perovskite band gap and perovskite shallow acceptor density. Features such as ETL thickness, HCl thickness, and HCl acceptor density had comparatively minor contributions. This results underscore the critical impact of ETL composition and doping on photovoltaic performance, while also pointing the secondary roles for the perovskite absorber and Hall transport rails. This figure presents the residual analysis for the implemented deep neural network model. The mean residual was relatively low at 0.0865, suggesting minimal bias in predictions. The residual exhibited a standard deviation of 0.5239, indicating moderate spread around the actual values. Furthermore, the model achieved a mean absolute error of 0.31162 and a root mean squared error of 0.5286, both of which confirm the model's high accuracy and generalization ability in prediction device efficiency. From the results, we can draw several insights. First, band gap tuning is crucial as it directly affects VOC and overall efficiency. And its donor concentration are the most critical design factors. Third, while HTL does have an effect, it is less influential compared to the ETL. And finally, the deep learning model provides both accurate predictions and explainability, making it a valuable tool for device design. To conclude, the farmadienium cesium tin triodide is a strong candidate for lead-free perovskite solar cells. By combining the SCAPS-1D simulations with deep learning, we can predict performance and guide the device optimization. Our analysis shows that ETL properties dominate performance. Effective pathway to improve efficiency. This approach not only accelerates research, but also reduces experimental costs. Thank you for your attention.
Let's see if you have any questions.
Where did you get the database to train the network?
The question is, where do you get the database for training?
From the we have get it from the SCAPS simulator.
Oh, but the database of data that you use for the deep learning.
Yes.
Yeah, where do you get the database?
where me get the data set database.
Yes.
We have changed all the parameters, the ETL type, the HTL type, the dopamine concentration in the perovskite, in the ETL, in the HTL, and we made a data set of 800 data. We use it in the deep learning. You hear me?
Are you happy with the answer?
Are you considering data from other places or other publications?
I don't understand.
Your parameters you use in simulations, you have taken from other publications or other sources?
No, it's our resources.
So your resources, like there is any base?
Like what?
Like you have means you have your imagination, or means you have taken from other?
No, not imagination, sir. It's we have changed the parameter of the solar cell in our simulator scopes.
Okay. So
And we get the fill factor, the efficiency, the GS the circuit current, and the open circuit voltage.
No, these are the output parameters, but input parameters, how you get it?
This data we have exploit this in a table, and my colleague Tarek Barghouth is his specialty in the science computer, employed it to explore the how which is the parameter most affected the efficiency in these parameters.
Okay, thank you.
Thank you. Now, please, can you show the last or the last
Last what?
the last slide where the key parameters.
The key parameters.
Yeah, the last almost the last slide.
In the slide of presentation.
Continue. The last one.
This one?
The key insights.
Key insights.
Yeah.
Training and analysis. Yes.
Yeah, this one. You say that the whole transport layer parameters are less significant, and I don't believe that. Okay, unless you have already parameters which are optimized for this layer. But if you have a given conductivity of this layer or a thickness of this layer, you will not get, and even the defects at the interface will become important. And so unless you have information about all these things for the HTL parameters, you can say that. But I don't believe that the parameters in the HTL layer become less significant.
From the simulation, we have changed 3 or 4 type of HTL and 3 or 4 type of ETLs with increasing the band gap of the absorber. We get for each value we get the VOC and the GSC and the fuel factor and the efficiency.
Okay. I think it would be good to revise, to review what you are doing, but I don't believe that the HTL parameters are less significant. Okay, thank you.
It's
So
less
let's-
significant, it's less significant, not the first. The ETL is most significant parameters with the band gap tuning.
Okay.
Yeah,
Thank you.
Yes.
Please check the STL results what you have obtained. Please check it and you can revise your results.
Okay, thank you. Let's thank the speaker.
Thank you, sir.
Before we finish this session, thank you for your. And it seems that the next one will be at
Ya me escuché.
8:30. Thank you.
45 minutos tenemos. Tenemos 45 para. ¿Quieren cambiar la contraseña o seguimos así?
Seguimos así. Sí, ya está funcionando bien.